In this lesson, I will talk about the memory hierarchy in current multicores, and I will do so while focusing on aspects which are mostly relevant to practical concurrency. If we look at a very abstract view of a computer, what we actually have is a CPU which performs operation on data which is stored in a storage medium and which is ideally infinite. Of course, in practice it is not that simple. In practical terms, we can view this abstract scheme as a core running operations on data stored on a disk. While this setting is very simple, it has various problems. The most important of these problems is the discrepancy between the speed of operation of the core and the speed at which the disk operates. So in modern processors, a core generally takes less than half a nanosecond to execute an instruction. On the other hand, in order to access data from the disk, we need more than a millisecond. What this means is that we have a 6 orders of magnitude difference between the speed of the CPU core and the speed of the disk. In order to solve this discrepancy, the used method is to place an intermediate level of storage between the core and the disk. In our case, that's called the memory. While this intermediate level of memory is smaller than the disk in terms of capacity, it is much faster. We can access memory in about 100 nanoseconds. Nevertheless, this is still slower than the speed of the core. A core will still have to stall for about 200 cycles before it can fetch data from main memory. Therefore, we apply the previously described pattern once more. We again introduce a smaller but faster level of storage between the main memory and the core. This is called the cache. And this pattern of introducing smaller but faster storage between the core and the previously existing level of storage is applied multiple times within the cache. In modern processors, we have 3 levels of cache, each smaller than the lower level but faster. So the last level of cache, or the L3 cache, can be accessed in 20 nanoseconds. That is significantly faster than main memory. The level 2 cache can be accessed even faster, in just 7 nanoseconds. The first level of cache, the L1 cache, can be accessed in only 1 nanosecond. That means that the core has to wait only a handful of cycles before it can fetch the data from that L1 cache. So what we notice is that as we go from the disk to the L1 cache, the access of the speed to data increases. We have lower and lower latencies. Of course, on the other hand, the capacity of these memory levels decreases. In a typical configuration, the disk can store terabytes of data. The main memory can hold, say, of the order of gigabytes. A configuration with 64 gigabytes is not uncommon. The level 3 cache in an Intel machine, for example, is 24 megabytes, the L2 has 256 kilobytes, while the L1 only stores 32 kilobytes of data. Therefore, we notice that as we go from the core towards the disk, the size of the memory layers decreases. In this case, one might ask the question, how is it possible that when we're working with terabytes of data, a cache of only 32 kilobytes can help us improve performance? Well, the reason this happens is due to what is called locality. We tend to access the same data over and over again. In addition, we tend to access data that's stored closely nearby. However, locality is a complex enough subject which will be discussed in another video. Notice that until now, I only mentioned the existence of one core. However, in today's machines, we have multiple such processing units. Basically, every machine, from smartphones to servers in warehouses, use multiple cores. A typical server configuration has 8 cores. As previously mentioned, each of these cores have L1 and L2 caches. In this case, these are separate for each of the cores. However, the third level of cache is shared between all the cores on a chip. The same can be said for all the layers below the L3 cache, the main memory and the disk. The fact that the L1 and L2 caches are private to each core leads to further complications. For example, multiple L1 caches can store a copy of the same memory address, possibly in different states and containing different values. This problem is solved through mechanisms such as cache coherence, which are not discussed in this video. Of course, sometimes it happens that the 8 cores, which were shown in the previous example, are not sufficient for our needs. We might need more cores, or we might need more memory bandwidth. In that case, what happens is we put multiple chips in the same machine. As previously described, if each of these chips has its own cores with its L1, L2 and L3 caches and an associated memory module. These chips are connected between each other using a high-speed interconnect. Of course, this adds extra latency. If we want to access data from another chip, we will have to add the latency needed to traverse the interconnect. A typical value for this latency is around 40 nanoseconds. Therefore, we can notice that it is significantly faster to access data which is stored within our chip than to access data which is stored in another chip or in memory connected to another chip. Therefore, these types of architectures are referred to as non-uniform memory access machines, or NUMA in short. Such machines are very common, particularly in the case of servers. To conclude, in this presentation we have seen how the memory hierarchy is structured in modern multicores. When working on concurrent programs, this may have a high impact, in particular from the point of view of performance.